Okay, I think that it's time to start. We cannot wait for a few more minutes. I think there is really not much need for an introduction. If you are here, probably it's because you want to listen to Steve Weinberg. If that's not the case, you should really empty the seat because there are many people waiting outside. Steve Weinberg, as you know, is one of the architects of the Standard Model. He's probably one of the deepest physicists we've had in the last 100 years. And in fact, not only he's a great physicist, but he's a great communicator. In fact, some of his books, you probably know, like The First 3 Minutes, Facing Up, Dreams of a Final Theory, and a few that are about to come, as he was telling us at lunch. So without further ado, I would like to introduce Steve Weinberg. He will be speaking about quantum field theory, fundamental or composite.
Well, thank you very much, Luis. It's a great pleasure to be back at CERN, a place I've visited, of course, a number of times before, although not often enough. I think since this is an experimental laboratory that I should show at least one curve of data. And so this is the price of shares of stock in quantum field theory if it were traded on Wall Street. And as you see, it's like many other shares of stock, it has gone up and down. The initial public offering was in the late 1920s when the recently developed quantum mechanics was applied to the electromagnetic field. And originally, quantum field theory was just the theory of the quantum theory of the electromagnetic field. Dirac had the vision of a theory of relativistic wave equations for particles like the electron and a quantum field theory for the electromagnetic field. To my mind, a rather unattractive, dualistic approach to physics, and I think throughout most of his life maintained that point of view. Pauli, on the other hand, was instrumental in bringing about a thorough quantum field theory. Everything, every particle is a quantum of some field. The photon is a quantum of the electromagnetic field. The electron is a quantum of the electron field. And there really is not a fundamental distinction between particles like the electron and fields like the electromagnetic field. Well, just as soon as quantum field theory in this sense was being born, it ran into a problem. Around 1930. Oppenheimer and Waller in 1930 discovered that when you tried to push quantum field theory of electrons and photons beyond the lowest order of approximation in calculating the energy of an electron, either a bound electron in Oppenheimer's work or a free electron in Waller's work, that you found you get an integral over the momentum of the virtual photon, which diverged at high momentum. And this was called an ultraviolet divergence or ultraviolet catastrophe. As a result, the judgment of the physics community on quantum field theory began to decline. And Oppenheimer, in particular, was influential in arguing that quantum field theory simply could not be trusted beyond the lowest approximation or trusted at all at energies that are high. And in those days, high energies meant more than a few MeV. And during the 1930s and early 1940s, shares of stock in quantum field theory continued to decline. And then in the late 1940s, a new optimism arose with the invention of a relativistic perturbation theory, which made it possible to see that all the infinities in quantum field theory could be absorbed into a redefinition of parameters like the mass of the electron and the charge of the electron. Now, some theorists thought that this was just sweeping the infinities under the rug. I think Dirac said something to that effect. When I was a graduate student in the early 1950s, late 1950s, I thought this was really wonderful because it wasn't just a way of eliminating the infinities in a theory, it was a way of selecting the right theory. As far as we knew at the time, this renormalization procedure, that is, absorbing the infinities into a redefinition of the constants of the theory, would only work for a very limited class of theories, so-called renormalizable theories. These were theories in which all of the parameters appearing in the field equations, like the charge of the electron or the mass of the electron, either were dimensionless, and I'm always thinking in physics units where the Planck's constant and the speed of light are 1, so that all dimensions are just powers of mass. They were either dimensionless, like the charge of the electron, e squared over 4 pi is 1 over 137, or had dimensions which are positive powers of mass, like the electron mass itself. But no parameters with negative powers of mass as their dimensionality. That allowed only a very limited class of theories, which you might think would be a drawback, but to me it seemed wonderful because that meant that we could understand why quantum electrodynamics was the way it was. For example, there's nothing in the symmetries of quantum electrodynamics, Lorentz invariance, gauge invariance, and so on, which rules out putting a term in the field equations or the Lagrangian which could make the magnetic moment of the electron anything you want. It was a great triumph of Julian Schwinger to calculate the corrections, the alpha over 2 pi correction to the magnetic moment of the electron and show that it gave the right answer. But in fact, you could have gotten any answer by putting in a term in the Lagrangian to add to the magnetic moment of the electron. However, such a term would have the dimensions of mass to the power -1. Those are the dimensions of the magnetic moment, and would therefore make the theory non-renormalizable. And so there was a rationale for the simplest version of quantum electrodynamics in which, in fact, the gyromagnetic ratio of the electron is 2 with a correction 1 plus alpha over 2 pi calculated by Schwinger. And I thought that was great. Optimism about quantum field theory rose rapidly and then again began to sink because after the initial success of quantum field theory in accounting for the theory of electrons and photons, it was natural to try to apply it to the strong interactions and the weak interactions. It was not possible to find any renormalizable theory at the time of the weak interactions. The Fermi coupling constant of beta decay has the dimensions mass to the -2. It's equal to about 10 to the -5 proton masses to the -2, which makes it a non-renormalizable theory, a theory in which this cancellation of infinities wouldn't work. And no one knew how to make a renormalizable theory, so that although the Fermi theory of beta decay worked very well in accounting for beta decay, when carried beyond the lowest approximation, it gave nonsense. It gave infinite decay rates. For the strong interactions, it was possible to invent a renormalizable theory, the old pseudoscalar meson theory, but it was very soon realized that the coupling in this theory was so strong that you couldn't justify the use of perturbation theory, and if you tried to get by with just the lowest order of perturbation theory, you got conflict with experiment. You could adjust the coupling constant to give the right cross-section for pion-nucleon scattering at low energy, but then you got the wrong result for pion photo production. And so it just didn't work. And as a result, during this period from, I would say from about the early 1950s until the late 1960s, there was another decline in our feelings about quantum field theory. And during this period, a number of ideas were introduced that would dispense with quantum field theory. One of them was S-matrix theory. Another was current algebra. And I will come back to both of them in the rest of my discussion. But starting in the late 1960s, and then accelerating in the 1970s, our optimism about quantum field theory once again returned with the advent of the Standard Model, first of electromagnetic and weak interactions, and then quantum chromodynamics for the strong interactions. And quantum field theory became the tool of choice for doing calculations in particle physics. I gave a talk at Harvard called The Renaissance of Quantum Field Theory in the early 1970s during this period of rapid increase. After about 1980s, it became clear quantum field theory would always be with us. This is the way we do calculations at the energies which are accessible in accelerators, and it works, and we certainly will stay with it. But there began to be doubts whether or not this was truly a fundamental theory or just an effective field theory. In fact, I should say just the first term in an effective field theory in which every possible interaction allowed by symmetries appears, the non-renormalizable as well as the renormalizable ones, perhaps a theory which arises from a deeper underlying theory which might not even be a quantum field theory at all. And of course, I'm thinking about string theory. It began to be thought that not only the Standard Model, but Einstein's general theory of relativity were just low-energy approximations to a deeper underlying theory, which, as I say, may not be a quantum field theory. In just recently, the last year or two, although maybe I've drawn the slope too steep, there's some slight reason for renewed hope that maybe this theory, general relativity plus the Standard Model, probably plus some other ingredients, but of quantum field theory, may in fact be all we need. And what I want to do in the talk, in the few minutes remaining, is to describe what I mean by an effective field theory. I just was at a conference in Bern on this subject where I was asked to reminisce about the developments which led to a paper I wrote on effective field theory in 1979, 30 years ago. And what I'd like to do is give a briefer version of those reminiscences with the apology that I'll be largely talking about my own development of ideas and my own work. I want to try to describe the confusion out of which this idea of effective field theory arose, and there's no one who can testify better than I can about how confused I was. Well, that's my excuse anyway. And then, after discussing what I mean by effective field theory and why we think that general relativity and the Standard Model are a low-energy approximation to a much more complicated effective field theory, I'll try to say why there's some room for optimism that this theory is perhaps all there is. I have to go back to current algebra, which I've already mentioned, because that's where it all started. As everyone knows or should know, this began with an idea of Nambu. In 1960, Nambu proposed that the axial vector current of beta decay is actually a conserved current, like the electromagnetic current, in a limit in which the pion mass, which is the lightest of all the hadrons, is zero. The pion is the lightest of all the hadrons. And he was able to use this idea to give a convincing derivation as an exact formula in the limit of zero pion mass of a formula that had been worked out by Goldberger and Schliemann for the pion decay amplitude. This is the Goldberger-Schliemann relation, where f pi is the pion decay amplitude, Ga is the axial vector current of beta decay, G pi is the pion-nucleon coupling constant, and Mn is the nucleon mass. It was soon realized that this hypothesis of Nambu would arise naturally in a theory where the underlying theory has an approximate symmetry, some symmetry, it wasn't clear what it was at first, which is not only an approximate symmetry of the field equations or the Lagrangian, but is spontaneously broken. That is, it's not respected by the ground state, the vacuum. In such a theory, as was soon realized by Goldstone and Nambu, there would necessarily be particles which are massless, except that the symmetry is not exact, so they're not massless, they're only rather light, and that was what was identified as the pion. The pion is what we call today a Goldstone boson or a Nambu-Goldstone boson. Nambu and his collaborators were able to use these ideas to give formulas for the rate of emission of a single pion of low energy in a variety of different collisions in 1962. However, more was needed to deal with processes that involve two low-energy pions, as, for example, pion-nucleon scattering, where a low-energy pion comes in and a low-energy pion goes out. For that, you need not only the fact that the current is conserved, but you need to know the commutation relations of the currents. And the technology was developed, I think named by Gelman, current algebra, for using the current commutation relations and the conservation of the current to derive formulas for processes involving multiple low-energy pions. This technology had a great triumph when Adler and Weisberger independently used it to derive a sum rule for the axial vector coupling constant of beta decay. Since this involved the commutators of the currents with each other, it did depend on the nature of the underlying symmetry, which Nambu's work had not depended on. And the fact that the axial vector coupling constant is greater than 1 rather than less than 1 showed that the underlying symmetry is a group SU2 cross SU2, which is, at least as far as current commutation relations are concerned, is the same as the group of rotations in Euclidean 4 dimensions, SO4. I started working on current algebra, for want of anything better to do, in 1965, and it seemed to me from the beginning that despite the great success of the Adler-Weisberger sum rule and the Goldberger-Triemann formula, this formula, there was rather too much emphasis here on the fact that the axial vector current was the current that appears in beta decay. I mean, that was interesting and important, and it led to these important results. But it seemed to me, after all, if the strong interactions have a SU2 cross SU2 symmetry, which is approximate as far as the field equations, but is also strongly broken by the vacuum state, that's an awfully important fact about the strong interactions by themselves. It would be important even if there were no weak interactions. And so I set out to see what this hypothesis would imply about purely hadronic processes. And I was able to derive formulas for the scattering lengths for low-energy pion-nucleon and pi-pi scattering, also for pi-nucleon scattering independently derived by Tomozawa. And as far as we could tell from the experiments of the time, these were successful. The experiments have gotten much, much better, and we've learned how to calculate corrections to these, and right now the agreement between theory and observation, which was reviewed at the conference in Bern, is really quite exceptional. Now, I then gave myself a homework problem. It's raining. Oh, I can see there's glass up there. Good. I gave myself a homework problem of calculating, in the limit of 0 pion mass, the amplitude for emitting an arbitrary number of soft pions in an arbitrary hadronic collision. This was not an urgent problem, and it was just a problem I invented for myself. The reason I wanted to work on this was that I had, a few years earlier, derived formulas for the amplitude for emission of an arbitrary number of low-energy gravitons or photons in an arbitrary collision. And I wanted to see, and got very simple results, and I wanted to see whether anything like that would come for an arbitrary number of soft pions. And I very soon ran onto the fact that the non-zero commutation relations of these currents, the axial vector current and similarly the vector current of beta decay, made the calculations just incredibly complicated, and I could get nothing simple. One day, late in 1966, I was sitting in an ice cream parlor in Harvard Square. Some of you may remember Brigham's, long gone. And I was doodling on a napkin the formulas for emitting 3 soft pions that I had derived using current algebra. And it suddenly occurred to me that those formulas look very much like you would get from a Lagrangian. Now that was surprising to me because in these days, in the mid or late 1960s, we had pretty well given up on the idea of using Lagrangians and specific quantum field theories to do serious calculations in hadronic physics. It had failed so miserably in the 1950s. And yet here it seemed that current algebra was producing results that looked like you would get them from a Lagrangian. In fact, I worked out a Lagrangian which I could show using current algebra would give precisely the results of current algebra. This is the Lagrangian. As you see, it's highly nonlinear. You have things like 1 plus pion field square over the pion decay amplitude square to the -2. So that's an infinite power series in the pion field times 2 terms involving derivatives of the pion fields, and likewise terms with the nucleon, anti-nucleon fields interacting with arbitrary numbers of pions. And there was a term that produced a pion mass, and it too was a power series in the pion field. But this I could show would be, although I couldn't evaluate what the amplitude was, this would be guaranteed to generate the same S-matrix elements as guaranteed by current algebra in the lowest order of approximation. The justification for this Lagrangian was simply that it satisfied all the axioms of current algebra. It had this symmetry, weakly broken by a term which it generated a pion mass. And furthermore, current algebra shows that the results for emitting n soft pions are of order the pion-nucleon coupling constant to the power n. In other words, are of lowest order in the pion-nucleon coupling constant, except that you have to put in the right answer for the axial vector coupling constant. You have to put in various factors of this. Originally, this Lagrangian was taken from a renormalizable theory with the factors of the axial vector coupling constant put in by hand as dictated by current algebra. But in any case, there was no justification for this except for current algebra. Then Julian Schwinger, a few months later, made a remark to me that I could save all the hard work I had done by just recognizing that the pion field had a simple transformation property under this SU2 cross SU2 symmetry. And he didn't know what it was, but he was sure it had some, and that I ought to be able to derive the structure of the Lagrangian on that basis. I spent the summer of 1967 on Cape Cod working out what the transformation of the pion field would have to be under SU2 cross SU2, assuming that it transforms in the usual way under isotopic spin rotations. And it turned out the answer was unique, up to a possible redefinition of the pion field. This is the unique nonlinear transformation property of the pion field. And that is the change when you make an SO4 rotation in the A4 plane, where A is 1, 2, or 3, the change in pi sub b, where b is 1, 2, or 3, is given by this formula, and the change in any other field, psi, that has isospin matrix T, is just an ordinary isospin rotation, but with an angle and an axis of rotation which is proportional to the pion field. This was soon generalized by Callan, Coleman, Wesson, Zumino to a general spontaneous symmetry breakdown, a general group G breaking to an arbitrary one of its subgroups, H. And the crucial point is, in both the general case and the specific case of SU2 cross SU2, that since the Lagrangian is invariant under SO4 rotations, this pion field, which actually just represents an SO4 rotation angle, like the Euler angles for ordinary rotations, would not appear in the Lagrangian if it were space-time independent. And so it can only appear wherever it appears accompanied by at least one derivative. And that was what was responsible to, that was what gave rise to this pseudo-vector coupling, which was essential in reproducing the results of current algebra. Now, after this work, I'm now taking it up to the late 1960s, my attention and the attention of a lot of other theorists was diverted to the development and the working out the consequences of the standard model of electroweak and strong interactions. And all this work on low-energy pion physics was put somewhat in the background, although it continued, and there continued to be both experimental and theoretical work in this area. And I'd say by the mid-1970s, the standard model had been almost completely developed and was already well, part of it was well verified by experiments here at CERN in the discovery of neutral currents. One of the things that excited me about the standard model is that it provided a rational basis for this work on current algebra. Quantum chromodynamics, if you limit yourself to renormalizable terms in the Lagrangian, it cannot be complicated enough to violate the symmetry SU3 cross SU2 cross U1. SU2 cross U1 is the, well, I'm sorry. I got carried away. SU3 cross SU3 cross U1 of baryon number. For a moment I was thinking of something else. The SU3 cross SU3 is the symmetry that we use to describe not only soft pions but soft K and soft eta mesons. And U1b is baryon number conservation, broken only by the up-down and strange quark masses. With SU2 cross SU2, the symmetry of current algebra at the beginning, broken only by the up and down quark masses. Furthermore, the electroweak theory dictated that the W, the Z, and the photon, in fact, coupled to just the currents, the conserved currents of this symmetry. So current algebra, and in particular the phenomenological Lagrangian that I had derived to save all the work of current algebra, was looking better and better. But at the same time, the success of the standard model highlighted the importance of renormalization theory, because it was only renormalization, the fact that the couplings are renormalizable, that allowed you to derive these consequences, or indeed any consequences. And the chiral Lagrangians are irretrievably non-renormalizable. There is no, whoops. Does someone know how to get the thing back? I guess I have to, I know what I have to do. I can do it, I can do it. I have to put my glasses on, though, to recognize the icon.
That was my problem, too.
There it is, there it is. Double click, okay. Okay, and now rapidly. Oh, by the way, I wanted to mention for this Lagrangian, after deriving it, I then went back and recalculated the pion-pion scattering and the pion-nucleon scattering lengths with about 1/10 the effort that I had used, it's an approximate number, in using current algebra. It was clear that this was infinitely easier than using the original technology of current algebra. But although the standard model actually validated that phenomenological Lagrangian, at the same time, it showed that it couldn't be used beyond the leading term, the so-called tree approximation, because it was hopelessly non-renormalizable. As you see, all of these terms have coefficients, all of the interaction terms have coefficients which are powers of 1 over f pi. So they all have dimensionality which are negative powers of mass. F pi is about 184 MeV. So 1 over f pi is a negative power of mass. And so all of these terms that involve interactions are terribly non-renormalizable. So the experience with the standard model reinforced the idea that this should only be used in the lowest order of approximation. And that's what I say here. And furthermore, that the justification ultimately would have to be found in the technology of current algebra. Even though it provided a better way of doing calculations, we could still only use it because of current algebra, because we knew it reproduced the same results as current algebra, but much more easily. Now, my thinking about that point which I just made began to change in 1976. And I can date it precisely because in 1976 I was invited to Eritrea to give lectures at the summer school there. And I decided, since I was very interested in the theory of critical phenomena that had been worked out by Wilson and Fisher and others in the few years before that, that a good way to learn the subject would be to volunteer to give lectures about it. And so I gave a course of lectures on critical phenomena, and I was very taken with Wilson's idea of, in studying energy, in condensed matter physics, we talk about wave number. In studying phenomena at low wave number, you can integrate out the short distance degrees of freedom and get a theory which you can use to study what happens at long wavelength, low wave number. Of course, in such a theory, once you integrate out the short wavelength degrees of freedom, the theory you get is a theory which is no longer simple. It contains every possible interaction allowed by the symmetries of the theory. But it has a cutoff, whatever your scale above which in wave number you are eliminating the degrees of freedom. So the coupling parameters in the theory will depend on that cutoff scale in just such a way as to make the physics independent of the cutoff. I call this the floating cutoff, or Wilsonian cutoff. Now, I soon realized, in fact, that if you're going to take a theory like this in which every possible interaction appears, it doesn't really matter whether the underlying theory is renormalizable or not. Even if you start with a renormalizable theory, once you start integrating out short wavelength degrees of freedom, you get this complicated theory including every possible interaction, renormalizable or not. And furthermore, you don't really even need to think about a cutoff, because with every interaction present that's allowed by the symmetries of the theory, for every infinity there will always be some coupling constant parameter which can be used to cancel that infinity, to absorb the coupling. In other words, non-renormalizable theories are just as renormalizable as renormalizable theories. And I wrote a paper in 1979 in which I proposed looking at the theory of pions, low-energy pions, the so-called chiral dynamics, in this way. every possible interaction between pions and nucleons allowed by chiral symmetry in this broken sense where the pion transforms nonlinearly would be allowed in the Lagrangian. So how could you do any calculation? I mean, what good is such a Lagrangian? Well, if you are working at low momentum, I say here kinetic energy, I really should have said momentum, that's the relevant thing. If you're working at low momentum, you can count the number of powers of momentum. Obviously, the leading terms are the ones with the smallest number of powers of momentum. The number of powers of momentum in any diagram, it's just simple arithmetic, is given by twice the number of loops plus 2 minus the number of external nucleon lines over 2 plus a sum over all the different types of interaction vertex. V sub I is the number of vertices of type I, and then it has a coefficient which is an index, I sub I minus 2, where I sub I, the index, is the number of derivatives in the interaction plus half the number of nucleon fields in the interaction plus the number of powers of pion mass, or in other words, half the number of powers of quark mass, since the pion mass square is a linear combination of quark masses. And now the thing that makes the whole thing work and useful is the fact that according to chiral symmetry, there are no interactions with I sub I less than 2. So therefore, as you add more and more interactions, you never decrease the value of nu. And if I sub I is greater than 2, you increase it, which means you get a smaller result if the kinetic energy, or actually the momentum, is small. So you could, in other words, use the kind of Lagrangian that I had on a previous slide, but supplemented with every possible interaction allowed by the chiral symmetry. You could use that to calculate scattering amplitudes to any given order in external momenta. To any given order, you will need a finite number of vertices with index greater than 2 to serve as counter terms for the infinities, but they would be there. This counting shows that whenever an infinity appears, there's a coupling, a new coupling, which can cancel it. For example, the leading terms are simply the terms with no loops and any number of vertices with index 2, and those are just the ones on the previous slide. The first corrections are those with no loops and any number of vertices with index 2 and one vertex with index 3. That's the so-called sigma term, still no loops. The next correction are those, and now we're talking about second order in the small momenta of the pions and nucleons. The next correction, any number of vertices with index 2, and either no loops and 2 vertices with index 3, which isn't very interesting, or 1 loop and no new vertices, or no loops and 1 vertex with index 4, which acts as a counter term to the loop diagram in item number 2. So in other words, you could use this theory to generate a perfectly finite, well-defined power series in the small momenta, and to any given order, you would only need to know a finite number of free parameters. That's all very well, but why should you believe this? I mean, this involving loop diagrams, it would be, I wouldn't have any idea how to justify this calculation on the basis of current algebra, how to use current algebra to validate calculations involving loop graphs. Pagels and his collaborators tried to do something like that before this was done, using just unitarity, but it was very complicated and there wasn't a systematic way of going about it. But there is a way of approaching this. For years, I had been teaching courses in quantum field theory and always emphasizing to my students that as long as you insist that you have Lorentz invariance and unitarity of the S matrix and a more technical property called cluster decomposition, which says that distant experiments give uncorrelated results, at least in theories unlike string theory, where you have a finite number of particle types, you are inevitably led to quantum field theory. That's the way I introduce quantum field theory in volume 1 of my books on quantum field theory. It's not very good pedagogy, but I do it that way because I want to give the reader an idea of why quantum field theory is the way it is. And in my 1979 paper, which I mentioned earlier, I enshrined this point of view as a folk theorem. If one writes down the most general possible Lagrangian, including all terms consistent with assumed symmetry principles, and then calculates matrix elements with this Lagrangian to any given order of perturbation theory, the result will simply be the most general possible S matrix consistent with analyticity, perturbative unitarity, cluster decomposition, and the assumed symmetry properties. Or to put it more briefly, individual quantum field theories have content. Quantum field theory itself has no content beyond unitarity, Lorentz invariance, and so on. Current algebra is not needed. There was a delicious irony in this. I had been at Berkeley in the early 1960s and the late 50s when quantum field theory had been pretty well abandoned in favor of something called S-matrix theory. The idea of S-matrix theory is, following good, logical, positivist principles, you should only concern yourself in physical theories with things that can be observed. You can observe S-matrix elements. They give you the probabilities of various collisions. So you should make a theory for physics which involves only statements about the S-matrix. And the statements they made were things like cluster decomposition, Lorentz invariance, unitarity, certain assumptions about the smoothness of the S-matrix as a function of the momenta. That was what was called S-matrix theory. I was at Berkeley, and I thought this was really an admirable philosophy, but I also thought that the S-matrix theorists really had no good idea of how to do calculations. I mean, they were deeply involved in things like the theory of many complex variables, which I knew I would never understand. And and they got nowhere with real calculations. And so I worked on other things like current algebra. Now, in 1979, it turns out that, in fact, the S-matrix theorists are right. What you need to impose is not any one specific quantum field theory, but just the general principles of Lorentz invariance, analyticity, cluster decomposition, and so on, plus symmetries, including Lorentz invariance, and in this case, chiral symmetry, SU2 cross SU2. But the way of implementing these assumptions of S-matrix theory was nothing but quantum field theory, which the S-matrix theorists had wanted to eliminate. And so things go around. And, well, after this work of mine in 1979, much work was done by a number of theorists, notably Gasser and Leutwiler, also Meissner, and many others, and that kind of work was discussed at this conference in Bern. It's become a whole industry, and my own work in the effective field theory of strong interactions was limited to theories of isotopic spin breaking and nuclear forces. And I think I probably don't have time for that. Luis, how much time do I have left? 20 minutes. Well, I'll say very briefly that in 1977, I calculated the light quark mass ratios, and I found, somewhat to my surprise, the down quark was almost twice as heavy as the up quark, which means that these, as I said earlier, these quarks' masses are what break chiral SU2 cross SU2. And it turns out they break isotopic spin conservation just as strongly, pretty much, as they break the chiral symmetry, so that the effective Lagrangian that I wrote down needs to be supplemented by additional isotopic spin breaking terms. Now, the quark mass terms in the Lagrangian of QCD take the form not just of the fourth component of a chiral 4 vector, but also the third component of another chiral 4 vector, which is proportional to the difference of the quark masses. And you see that is just the quark T3 antiquark. And as a result, the chiral Lagrangian has to contain the most general terms which are invariant under isospin, and those are the red terms here, but also terms which transform like the third component of a chiral 4 vector, and those are the purple terms here. And there are 4 constants here, not just one. And we know the value of B, theoretically, it's minus 2.5 MeV. It's harder to calculate the other coefficients, and I don't know what progress has been made on this because I haven't kept up with it. I think this was actually first worked out in my volume 2 of my quantum field theory book. The other area that I worked in was nuclear forces. I gave a talk very much like I've given here to my class in quantum field theory, and I said the leading terms are terms with 0 loops and all the interactions having index 2. And then I listed the terms with index 2, and they're the same ones that I listed before and that appeared in that slide earlier in the Lagrangian I wrote down. But then it suddenly occurred to me while I was standing at the blackboard that there's another term with index 2. It's a term with no derivatives and no powers of the pion mass, and therefore, according to the rules of chiral symmetry, no pion fields at all, but 4 nucleon fields. You see 0 plus 4 over 2 plus 0 equals 2. No, that's not hard. And this, with 4 nucleon fields, that's in other words a nucleon-nucleon contact interaction, a Fermi interaction. And I knew that nuclear theorists for many years had known that in order to account for nuclear forces, pion exchange is not enough. You need just this kind of contact, hardcore interaction. And so I began to use this to develop a theory of nuclear forces. And I haven't done much on that, but other people have picked this up, Ordonez, Van Kolk, Fryer, and so on. And that, again, has become a big business. Now, the idea of effective field theory began to have implications in other areas. In particular, it was used by a number of authors. The one who I learned this from was Polchinski, to justify the approximations made by Bardeen, Cooper, and Schrieffer in their theory of superconductivity. You know, they used a very simple Hamiltonian, and I always wondered why that simple Hamiltonian would give results of such incredible precision, like the quantization of flux or the formula for the Josephson frequency at a Josephson junction. And for some reason, condensed matter physicists don't ask such questions. If they have a theory that works, they're happy. This work justified the approximations made by Bardeen, Cooper, and Schrieffer using the same kind of elementary counting of powers of wave number or momentum, except it wasn't momentum, it was the difference between the momentum and the Fermi surface momentum. And they showed that there's an effective field theory of which the leading term is the Bardeen-Cooper-Schrieffer term. There was also an application much more recently of effective field theory ideas last year by an interesting paper by Chung, Cremonilli, Fitzpatrick, Kaplan, and Senatori, showing how you could analyze very general theories of inflation where you have an effective field theory for the gravitational field and any number of inflaton fields. What concerns me in the rest of my talk, though, is the application to the Standard Model and to gravitation. Is the Standard Model all there is, at least for strong, weak, and electromagnetic forces, or do you have to include non-renormalizable terms as well? Remember, non-renormalizable terms are terms that are suppressed, are terms where the coupling constant is a negative power of mass. If that mass is a huge mass, then those terms are highly suppressed. which would account for the success of the renormalizable standard model, but at the same time suggest that there are small corrections that we ought to take into account. In particular, there are two reasons for suspecting that this is true. For one, there's evidence, at least a hint of evidence, of a higher mass scale that we have to take account of. The SU3, SU2, and U1 coupling constants, which are functions of the energy at which they're observed, they're called running coupling constants, when suitably normalized, become almost equal at an energy of the order of 10 to the 15 GeV. Or if you use supersymmetry, they become equal quite accurately at an energy of the order of 2 times 10 to the 16 GeV. And this suggests new physics at some very high energy like that, so that if there are non-renormalizable terms to be added to the leading terms in the standard model, they would have indeed very small effects. In particular, it seemed to me very important that the standard model, at least the renormalizable part of the standard model, the part where the coupling parameters are dimensionless or positive powers of mass, like masses, automatically conserves baryon on lepton number. That is, if you don't introduce supersymmetry. If you do introduce supersymmetry, oh, that's fun. If you do introduce supersymmetry, then this isn't true, but there's a version of supersymmetry called split supersymmetry in which it's still true. So either without supersymmetry or with split supersymmetry, which I won't go into, there's no need to assume baryon and lepton conservation as fundamental symmetries. They're automatic consequences of the standard model, and that suggests that they're not fundamental symmetries, and in fact, the higher non-renormalizable terms, there's no reason for them to conserve these symmetries. I pointed out that there was, in 1979, when I was thinking about these things, that there's a term with a dimension of mass to the -1, so suppressed by 1 power of some very high mass, involving 2 lepton doublets and 2 scalar doublets. And when the scalars get a non-vanishing vacuum expectation value, this produces a neutrino mass. And if you set the coupling parameter to be of order 1 and this mass to be of order 10 to the 16 GeV, you get neutrino masses of the order of 10 to the -2 volts, which we now know is right. I think the discovery of neutrino masses of this order suggests that these terms really are present in the Lagrangian, and therefore we have to think of the renormalizable standard model as just the first term in a much more complicated effective field theory. Similarly, as also pointed out by Wilczek, there's a term which violates baryon number as well as lepton number. It allows for the decay of the proton into anti-leptons, although not leptons. It's suppressed by 2 powers of mass and gives a very small proton decay rate, although one that is not impossible to detect. Now, of course, these kinds of interactions can be, and in fact, in 1979, they already had been derived from a grand unified theory by integrating out some of the heavy particles in that kind of theory. But the point is that you would expect them in any case, just on the basis that there's no reason to exclude them. There's no reason to believe baryon and lepton number are fundamental symmetries. And in fact, in string theory, it's really impossible for them to be fundamental symmetries. Now, that left the hippopotamus in the corner. The other force, which, as in chiral dynamics, there is no renormalizable term which can dominate and which we can calculate with at low energy, that is gravitation. From this point of view, and now thinking of it as a Wilsonian theory where I have a floating cutoff, we should really think of the action for gravitation as not just the cosmological constant and the Einstein-Hilbert term, but all possible terms. We can, if we like, introduce an ultraviolet cutoff with these coupling parameters being given a cutoff dependence which makes the physics independent of the cutoff. And this has been developed in the low momentum or large distance limit by especially by John Donahue and his collaborators. But with any such theory, as with chiral dynamics, you have a feeling that, well, it's not just a feeling, you can see that there's going to be problems in using this kind of theory to calculate at high energy. You wouldn't trust the Lagrangian I wrote down for pion and nucleon interactions at energies above about 2 pi f pi, which is roughly the nucleon mass, or about a GeV. I mean, in that case, the higher non-renormalizable interactions would be just as important as the renormalizable ones, and you couldn't use it at all. And we all know that in the strong interactions, at those energies, the relevant degrees of freedom are not pion fields and nucleon fields, but quarks and gluons, the quarks and gluons of quantum chromodynamics. In the same way, you normally wouldn't think you could use such an action except in the large distance limit, and the way Donahue did, and at very short distances where lambda, for example, has to be taken to be some very high energy like the Planck mass, you wouldn't think you could use an action like this at all. I can explain what goes wrong by using the Wilsonian version of the renormalization group equations. Instead of these parameters f, I can introduce dimensionless couplings by just putting in powers, suitable powers of the cutoff, so that all of these g's are dimensionless. And then lambda d by d lambda, g of lambda, which is also dimensionless, cannot depend on lambda itself, because there's no unit of mass to compare lambda with, so it can only depend on the g of lambdas. And this is the Wilsonian renormalization group equation. Now, perturbatively, you find the g of lambda, all but a few of them blow up as you go to large lambda. That's the symptom of the fact that these represent non-renormalizable couplings. And they may even become infinite at a finite value of cutoff. And that's been observed since 1955, when Landau observed a phenomenon like that in quantum electrodynamics at exponentially high energy. And there's also a corresponding phenomenon in scalar field theory called triviality, which means that because of that, you have to set the coupling equal 0, which makes it trivial. Now, we usually assume that this doesn't matter in general relativity, because before these couplings blow up, other degrees of freedom, like maybe strings, will become important, just as quarks and gluons become important, and they replace pion and nucleon fields in high energy in chiral dynamics. And now I'm going back to the point in the beginning of where I showed that curve of quantum field theory versus time, where it began to rise very recently. Maybe not. Maybe, in fact, nothing replaces the gravitational field and the fields of the standard model. Maybe what you see at low energy is what you get at high energy, and there's nothing new. I mean, if I had to bet, I would bet that's not the case. I would have to bet, my bet would be something on string theory. I'm not against string theory. I just want to raise this as a possibility we shouldn't forget, but not one that perhaps you would put your money on. But it's worth at least keeping an open mind about it. The theory will be safe from the couplings blowing up if these coupling parameters, if there's a value of the beta function where if there's a value of the couplings where all the beta functions vanish, and if the couplings are on a trajectory as defined by the renormalization group equation, this equation, if the couplings are on a trajectory which, according to this equation, is attracted to that value that I call G star. Now, an example of this is quantum chromodynamics, where there is a fixed point of the renormalization group equations. It happens to be at zero coupling, and the theory at high energy is not only safe from the couplings blowing up, but it's a free field theory, so we call it asymptotically free. Here, I'm proposing that the coupling is not zero. We know it can't be in general relativity because that's the case we can study. and it doesn't work, the couplings, the zero is definitely a very repulsive point in general relativity. But there may be a fixed point which is not at zero, and where you don't have asymptotic freedom, but you're safe from couplings blowing up, and that's called asymptotic safety. I suggested that in my Eritche lectures that I mentioned earlier in 1976. Now, the trajectories with the couplings approaching G star when the cutoff goes to infinity form a surface in the space of all couplings. It's called the ultraviolet critical surface. And you can think of the requirement that the couplings are on this surface as a physical requirement which must be imposed to prevent the couplings from blowing up in infinity in the same spirit that in the old days of quantum electrodynamics, we imposed the condition that the Lagrangian of quantum electrodynamics only contain renormalizable couplings. And so, for example, we were able, or Schwinger was able, to calculate the magnetic moment of the electron. So this is completely analogous to that very desirable feature of renormalizability, that is, there's a physical requirement that the couplings have to be on the ultraviolet critical surface. However, it's not that attractive unless the ultraviolet critical surface is finite dimensional. How much time? 2 minutes, good. Because only in the case where the coupling, where the ultraviolet critical surface is finite dimensional, do we have a theory like a renormalizable theory in which there are only a finite number of free parameters. So it becomes crucial to ask, what is the dimensionality of the ultraviolet critical surface? Now, that's determined by the behavior of the beta function near the fixed point. Near the fixed point, we don't expect any singularities, and the beta function should, since it's zero at the fixed point, near the fixed point, it just goes linearly in the difference between the couplings and the fixed point. The matrix is the matrix of partial derivatives, and the solution of that equation is trivial. The couplings just go to the fixed point with a distance which is just a sum of the cutoff to various powers, and these powers are just the eigenvalues of this matrix. Now, you can see that in order for this correction term to vanish when lambda goes to infinity, little lambda has to have negative real part. B is a real matrix, but it's not symmetric, so its eigenvalues are not necessarily real. They're either real or they come in complex conjugate pairs. The dimensionality of the ultraviolet critical surface is therefore equal to the number of eigenvalues of of B that have negative real part. Now, you might think, since N and M range over all possible interactions, B is an infinite dimensional matrix, you might think it would be a miracle if there were only a finite number of eigenvalues with negative real part. But in fact, it's quite common for that to happen. And an example of that is presented by the phenomenon of second-order phase transitions. As we learned from Wilson and company, when you have a second-order phase transition, there exists a fixed point of the effective field theory for the collective variables of the system with one infrared repulsive direction. And I know the number is 1 because with a second-order phase transition, you only need one parameter to be adjusted, like the temperature or the pressure, so that you eliminate the components of the trajectory along the infrared repulsive direction, and you get on an infrared attractive surface, the infrared critical surface, which has codimension 1. That is, its dimension is 1 less than the dimension of all the number of all the couplings. Well, obviously, if there's only one direction in which the couplings go to infinity when lambda goes to 0, that is the unique direction in which the couplings go to 0 when lambda goes to infinity. So this is a theory with a one-dimensional infrared ultraviolet critical surface. And for tricritical points, you have a two-dimensional ultraviolet critical surface. So the question is, what is the dimensionality of the ultraviolet critical surface for general relativity? Or I shouldn't say for general relativity, which is now passé, but for the quantum theory of gravity. I emphasize there's no conflict between quantum mechanics and gravitation. That general effective field theory is a perfectly good quantum field theory of gravitation. It's just that if you didn't have asymptotic safety, it would break down at high energy. With asymptotic safety, maybe it's a good theory even at high energy. Well, calculations have been done, starting with a paper I wrote in 1979, using a variety of methods to find the fixed points and assess the dimensionality of the ultraviolet critical surface for those fixed points. It started, I won't go through all this, it started with dimensional continuation, then the 1 over n expansion, where n is the number of matter fields you add, lattice quantization. The subject has been largely revived by Martin Reuter, who in 1998 started to apply a method called the truncated exact renormalization group. And I don't have time to explain that, but I will just say that the exact renormalization group are a set of exact equations which unfortunately relate all possible couplings in a way that doesn't allow you to solve any subset for any subset of the couplings. So what you have to do is truncate the equations by throwing away all but a finite number of couplings. And Reuter started this only keeping the Einstein-Hilbert term and the cosmological constant, and then other authors started to put in more terms. There have been a lot of papers on this. There's going to be a conference on this in the Perimeter Institute in this December. But for a long time, I ignored this work or just gave it a modicum of attention because it seemed to me the results were rather discouraging. With only 2 non-zero couplings, the dimensionality of the ultraviolet critical surface turned out to be 2. All directions were attracted to the fixed point. When they added a third interaction, like say r square, they found a 3-dimensional ultraviolet critical surface. Now, if this continued, and when they had 1,000 couplings, they had a 1,000-dimensional ultraviolet critical surface, so there'd be 1,000 free parameters in the theory, forget about it. The good news is last year, Codello, Percacci, and Ramadi did a calculation which they allowed up to 7 independent terms. They took the Lagrangian to be just powers of the curvature scalar, but the number of powers ranging from 0 up to a maximum, which could be anywhere from 2 to 6. So when it's 6, including n equals 0, there are 7 free parameters. And they found that although the space of coupling constants was 7-dimensional, there were still just 3 attractive directions. The ultraviolet critical surface was 3 dimensions. They then included matter, and they found that didn't change the results. Then another group, Benedetti, Machado, and Saueressig, considered another theory with 4 terms in the truncation, but a different 4, where the 4th one is the square of the Weil tensor. And again, they found just a 3-dimensional attractive surface. And the same if you add matter. These results suggest the existence of an asymptotically free, not free, that's a mistake, asymptotically safe quantum field theory of gravity with no problems at all in infinite energy and just 3 free parameters. 1 parameter, well, 2 parameters tell you which trajectory you're on in this 3-dimensional space, and the 3rd one tells you where you are on it for any given value of lambda. These eigenvalues, lambda, little lambda, actually seem to converge pretty well as you include more and more terms in the truncation. This is a table of the values obtained by Codello, Percacci, and Ramadi. If this pattern continues, then I think that would be very encouraging for a quantum theory of gravity, not based on string theory, but just based on good old quantum field theory. Now, what about applications of this? Well, fortunately, since I'm out of time, I haven't done much, but the obvious application is to the early universe, where the Hubble rate is very high, so that you might hope that you're taking a cutoff of that order of magnitude, that you're near the fixed point, and you can then test that idea and see whether it leads to a theory of inflation and also to a theory of how inflation ends. And my work on this is shown in these view graphs, and I'm glad I showed them, because the people who started work in this area were Bonanno and Reuter. But my own work shows that you can indeed do calculations in which apparently you get a sensible theory of inflation with an end to inflation when the couplings are driven away from the fixed point. When the Hubble rate becomes low enough so that at that value of lambda, the couplings are no longer near the fixed point, and then inflation is over. This is just the beginning of work, and obviously, for example, matter fields have to be introduced into this in a realistic way, which neither Bonanno and Reuter nor I have done. But I think it's worth pursuing. Who knows where this will lead? I don't want to discourage string theorists, but there's just a possibility that maybe that isn't the way the world is, and that the world is really much more like what we've always known, that is the standard model plus general relativity. Thank you.
Well, maybe we have time for one or two quick questions.
Can I ask a brief question?
Yeah.
Is the chiral Lagrangian asymptotically safe?
Oh, that's a good question. I've wondered whether there would be any reason derived from quantum chromodynamics, which after all has good behavior at high energy, why the effective field theory that describes it at low energy, the chiral dynamics, should have a fixed point which is ultraviolet attractive. And I have not been able to think of any reason why that should be true. I would love that to be true, but I cannot justify that to myself. If anyone has any good idea about that, I'd love to hear it.
Massimo?
Sorry. This model of inflation, if you want, where you have higher derivatives, right?
Yeah.
Reminds a little bit of the kind of old Starobinsky model, where you also had higher derivatives but no scalar field, like
Yeah. Yeah, he had just included an R square, I think, if I remember correctly. Yeah. Yes. Of course, I'm not doing that because I really think you have all of these terms. And I imagine that you have to include matter and not just rely on R squared to do it for you. I should say that that last reference I gave to Sauer-Essig and two other guys study the question of whether or not in this kind of theory there are ghost poles, which you often get when you include higher derivatives. And they conclude that there aren't in this kind of theory.
Okay, I guess we have to leave it at this. Let's thank our speaker again.
Thank you.